And here it is on my screen. You might have to expand some of the cells to make them big enough to read everything. Down here, degrees of freedom, it was cut off, so I kind of made that a little bit bigger. So what this is this is a little tool that I want to use to help you to get a really clear grasp on what standard deviation is, as well as variance and standard error. These are three important metrics of variation in the data. And now you all know how to calculate the median. We did that yesterday or Tuesday. I'm assuming you already know how to calculate a mean. A mode is just the count of the number of the value that occurs most often in the data. Those are the measures of central tendency. And it's easy to focus on those, but in statistics, the variation is just as important as that measure of central tendency. The center and the spread tells you what most of what you need to know about the data. So the key concept here is you want to know how far, on average, any data point is from the mean. So if you've got your mean, that's your center. How far away are all the data points from that? And the calculation that we use to do that is, we're going to see this over and over and over in the rest of the statistical test. And I'm not going to have you calculate them all by hand, but just a couple times so that you see this is what goes into it. Okay. So I have 4 different data sets that each have 5 data points. It's really simple. And it's here in the spreadsheet. You can do it. We'll do it together right now. All right. So let's imagine that we have 5 students, student 1, student 2, student 3, student 4, student 5. And they took a test and the first student got 5, the next one got 4, then 3, then 2, and then 1, right? So how many is that all together? You can just sum it up, equals sum, open parentheses, select all these values, close your parentheses and enter, right? And we don't want it to autofill, no thank you. And then your N. N is the symbol we use in stats to say the number of observations, the number of individuals, the number of samples. So here the N is 5. You could just type 5, or you could say equals count, select all of these scores, close parentheses, 5. Either way, that works. The mean is, as you know, just equal to the sum divided by N, right? 3. Or you could say equals average 3. All right, so our mean here is 3. Our degrees of freedom is equal to N minus 1. So you just say equals N minus 1. Or you could just type 4 because that's really simple, right? Now let's go up here. Now we've got the mean. This is the key thing that we need to go on to calculate the standard deviation, the mean and the N, right? So the difference from the mean of each point, we can easily calculate. You can do it in your head, or you can type out equals test score minus mean, right? So in this case, it's 2. I don't want to autofill in this case. It's going to give me the wrong answer, okay? And you can say equals test score minus mean, right? Or you can say, since you know the mean is 3, equals 3 minus 3. However you want to do it, that's fine. And there you get 0, right? And here you would say equals test score minus the mean equals test score minus the mean. There you go. And one thing I like about this really simple example is because the way I set it up, you can see how if you added up all these numbers, what do you get? 0, right? So if you wanted to understand the average distance and you just added them, you would get a nonsensical number, really. It's just 0, right? It's like 0 divided by the degrees of freedom. It makes sense. So what we do is we square them. We square the differences. So we're going to take the difference from the mean squared is what we're going to calculate in this next cell over here. So you just say equals 2, I think the little hat squared, does that do it? Yeah, that does it. And I don't actually want to autofill because I don't want to go all the way down. Or you can just say equals 1 times 1, or if you already know that 0 squared is 0, you can type that in. -1 squared is 1, -2 squared is 4, right? And then you take the sum of the squared differences, the sum of the squared differences. And so you just say equals sum, or you can add it up in your head, but there you go, 10, right? So the sum of the squared differences is 10. And our degrees of freedom, that was supposed to go here, the degrees of freedom is n-1, which is 4. Now to calculate the first variance metric, which is called variance, you just divide the sum of the squared differences by the degrees of freedom. Equals 10 divided by 4, 2.5. That's your variance, right? But wait, we want to talk about standard deviation. Variance is used a lot, but here we want to talk about standard deviation. Standard deviation is just the square root of variance. So you just say equals SQRT, that'll calculate the square root, open parentheses, 2.5, or select that cell with the variance, close parentheses, bingo, 1.58. Your standard deviation is 1.58. Your mean is 3, your standard deviation is 1.58. Now, there's a third really important variance metric I want you to know, and you're going to need to remember this, all of these, but you'll have to remember the formula for this one in particular. It's called the standard error, and it's often something that we use to put error bars on the graphs. We'll start doing that more soon. The way that's calculated is you take the standard deviation and you divide that by the square root of the number of samples. Standard deviation divided by the square root of n. So to do that, you just say equals standard deviation front slash divided by SQRT square root, open your parentheses, square root of n. There's your n, 5, close parentheses, bingo, there's your standard error. Right? So, what's that?
Real quick, can we go over the variance one more time? Was that it? Okay.
Okay. So to calculate the variance, all you do is you take the sum. All right, let's look at this formula real quick, where it says variance is equal to the sum of the difference in the data point minus the mean squared divided by n-1, which is degrees of freedom. So you say the sum of the difference of the squares here was 10. So that divided by n-1, your degrees of freedom, 4, is equal to 2.5. This divided by this, 10 divided by 4. The sum of the squared differences divided by the degrees of freedom is the variance. Any questions? We're going to do it again 3 more times. We're going to do it 3 more times. But first, I'd like to point out that notice that variance and standard deviation and standard error follow a pattern, right? They follow a pattern, right? The standard error is usually smaller, right? And also notice that these test scores vary a fair amount. They vary from, the range of them is from 1 to 5. The range is 4, right? So think about how much variance that is. You know, how much does that seem like that's really different? If you had a class and there were, let's say there were 5 students and there were 5 questions on the quiz and one of them got all of them right and one of them only got 1 right, you say there's a big difference in the ability of these students to do this quiz, right? Like some of them knew the answers and some of them did not, right? So that right away tells you that with a mean of 3, a standard deviation of 1.5 is a pretty big deviation, right? That's a pretty big variation in the scores of the students, right? Relative to the mean. Okay, so let's do the next one and we'll start looking at how that works out too. Again, we're going to go over here. We've got test scores. In this case, we had 5 students and 3 out of 5 of the students got a perfect score of 5 on that quiz. And 2 of them bombed it. Like they didn't show up, probably. That's what happened. They didn't get any of them right. Probably they didn't show up because how could you get them all wrong? So we're going to go ahead and do the same calculations. We're going to start by taking the sum of the scores equals sum. I'm going to select all these data points, close parentheses, and the sum here is 15. Same as the last one, right? So the total amount of points gained by the students was the same, but the distribution of scores was somewhat different, right? As you can see. The n, the number of scores is the same, 5, right? And the mean here, if we take equals 15 divided by 5, our mean is the same. Coincidence? Or was this part of my evil scheme? Okay. Now the difference from the mean, again, is calculated the same here as for the last example. You just say equals test score, that's your data point, minus the mean value of 3, right? Enter. Equals test point, test score, minus mean. Equals test score minus mean. Or you could even just say equals 0 minus 3. If that's easier, equals test score minus mean, right? And now you can see the differences from the mean. If you added these all up, what do they equal? 0, again. So in order to not have a 0 value, in order to make these all positive, we square them, multiply them by themselves. That's why we square them. Simple as that. So we just square them. Equals, we can just say 2 times 2, right? Or we can say equals 2, that little hat above the 6, 2, that's how you square something. Little hat 2 is to the power of 2. Equals, oops, 3 to the power of 2. Square it. Equals difference from the mean squared. Equals difference from the mean squared. Now we have the squared differences and we want to get the sum of the squared differences. So we just say equals sum squared differences. There we go, 30. So the sum of the squared differences is already a lot higher here than it was for the last example, right? Like this second quiz, there was a lot more variation. And you could see that from the raw numbers, right? You can kind of start to get the picture of how this works. Okay, now we want to calculate the degrees of freedom. So the degrees of freedom, again, is just n minus 1. N minus 1 for this. Degrees of freedom can be calculated differently for different tests. For this, it's n minus 1. So you just say equal to your n, 5, minus 1, it's 4. Same degrees of freedom, right? Now we want to calculate the variance. To calculate the variance, all we do is divide the sum of the square differences by the degrees of freedom. And our variance is 7.5, which is, again, a lot higher than our last example. Now to get the standard deviation, we just take the square root of the variance equals SQRT, open parentheses, select the cell with the variance, close the parentheses. There you go. And I might want to make fewer decimal places so I can see it more easily. Decrease decimal places. For some reason that's not working. Okay, so our standard deviation in this case is more like 2.7. That's a lot higher than before. And again, you can kind of see that reflected in the difference in these test scores where 3 out of 5 students got a perfect score, 2 totally bombed it. Whereas over here, some did really well, some did really badly, and a few did in between, right? This gives you an idea of how variance is. Now, the standard error, the nice thing about standard error is it kind of gives it scales it by the number of samples that you have, right? So if you have a lot of samples, it's going to bring that standard error down because you're dividing by the square root of n, which is a scaling factor. So here you're going to say equals standard deviation divided by SQRT, square root of n. Interesting. So in this case, what happens is our standard error is higher than the last sample, but we still get a lower standard error than we have variance. A lower standard error than variance or standard deviation. Each time you're sort of scaling it, right? Scaling it. So we'll go down to the next sample. Now in this case, we had a quiz where there were 10 possible points. One person, perfect score, nailed it. Another person, not so good, only 5 out of 10. And then 3 out of the 5 students apparently didn't show up to take it because they got 0, right? So what do you think is going to happen with the standard deviation? You think it's going to be higher than the last one or lower than the last one? I don't know if you can do thumbs up and thumbs down, right? What do you think? Think about it, okay? So let's go ahead and calculate it. We'll start by getting the average here. Equals sum of all the test scores. The n is equal to count of all the test scores, or 5. You can easily see that. But I'm showing you, so when you have more data, you can also do this with a ton of data that you don't want to count. And then the mean is equal to the sum divided by n, or you could calculate average and select the points. The degrees, all right, so now let's go up to get the difference from the mean. Again, we've got 10 minus the mean of 3, right? Same mean. Same mean. We're not finding differences in that central tendency. We're only finding differences in the variation at this point. Okay. Then we have again equals the test score minus the mean equals test score minus the mean equals test score minus the mean, and again equals test score minus the mean, which is almost like too obvious. Now, again, if you added all these up, what are you going to get? 0. You get the positives and negatives. It's always going to be like that. So you have to square them. So you say equal this little hat 2. That squares it. Now I am going to drag it down this time because that's just going to be easier. What I'm going to do is I'm going to select 49. I'm going to copy, and then I'm going to select the cells I want to paste it into, and Control V, I'm going to paste them in there. All right. So now I can see, well, we already know 7 squared is 49, 3 squared is 9, 2 squared is 4, etc. So now I'm going to add these up. Equals sum of these squared differences from the mean. And our sum of squared differences is 80. It's 80 now. Look, compare that to before when our sum of squared differences was 10 or 30, right? We have a lot more variation. The range goes from 10 to 0. That's a much bigger range. So our sum of square differences is also bigger. And now when we calculate the degrees of freedom, we already know that's going to be 4, right? That's equal to the number of samples minus 1. We already know that. And the variance, we've already done this before too. We know, we just have to say the variance is equal to the sum of squared differences divided by the degrees of freedom. Okay, our variance here is 20. Again, compare that to the previous examples where our variance was 2.5 or 7.5. Now we've got a lot higher variance. Even though the mean is the same, the variance is 20. It's all over the place, right? These scores are really all over the place. And the standard deviation now is you simply take, again, equal to the variance divided by SQRT, the square root of, I'm sorry, no, it's just equal to the square root. I'm like, what am I doing? Equal to, the variance is equal to the square root of the variance, equals SQRT variance, square root of variance, right? So our standard deviation here is 4 compared to before 1.5 or 2.7. And our standard error, we're going to take standard error is equal to the standard deviation divided by the square root of n. Here's our n. And we get 2. Our standard error is 2, which is still higher. It's still higher, but it doesn't scale as dramatically. It's sort of a more restrained variance measure. Okay, one more. Okay, one more. And I'm just going to do this. Let you do it on your own. I'm not going to talk it through. I'm just going to do it and you can watch and unless you've already done it, you've probably finished it and you're like checking your email. But in case you're not familiar with spreadsheets and you wanted some help in helping you through this. Okay, so equals, oh, we got to calculate the sum, equals sum, equals n, that's the count, equals sum divided by count, and then you have you get the mean, which is again 3. Oh no. Yeah, I designed this to do that on purpose. Why? Because I wanted to show you something about data. I wanted to show you something about data without even calculating it. What do you think is that the standard deviation? Is it going to be higher or lower? Just look at these scores. See how they range from 2 to 4, right? Everybody did like pretty average or pretty good. Nobody bombed it. Nobody aced it, right? So what are we going to get when we start calculating this? Equals difference from mean, test score minus the mean equals test score minus the mean equals test score minus mean equals test score minus the mean equals test score minus mean, and we get a sum of 0 for all of them. So again, we got to square them, equals difference from the mean at 2. That squares it. And you can take these and you can copy and paste them down. And then you can just sum up this column equals sum of the square differences. And our sum of square differences is now 2, which is the smallest so far. Again, look at these numbers. There's less variation, there's less range of these numbers than there were in the last 3 examples. Our degrees of freedom here is still going to be 4, just the number of samples minus 1. And the variance, again, is you just take the sum of the differences, the sum of the square differences divided by the degrees of freedom, and our variance is only 0.5, much, much lower. And our standard deviation is equal to the variance, the square root of the variance, and now that's less than 1, it's 0.7. And if we take our standard error, which is equal to the standard deviation divided by the square root of n, then it's only 0.31, right? It's a lot smaller. So the goal of this exercise was really to build your intuition about what variance is and start to really see that given these 4 different sets of numbers that all have the same mean, the same number of observations, but widely different variances, just kind of looking at it. This one ranges from 5 to 1, 0 to 5, 10 to 0, and these are all 2, 3, 4, right? And you can see the differences in the standard errors. You get much, much higher standard error when you have wider ranges of numbers. Okay, good.